Are you confused while writing the resonance structures of the resulting carbocation in the aromatic electrophilic substitution reactions of benzene? Then this video is for you. Most of the students, they mug up the resonance structures of carbocation in the electrophilic substitution reactions of benzene and they forget all of them right in the exam hall. But what if I tell you that there is a simple logic to remember all of them and it never fails? So stay with me till the end of this video because in next few minutes I'll show how effortlessly you can draw these resonance structures of carbocations. When you write the entire mechanism of nitration or any other electrophilic substitution reactions of benzene without showing resonance structures, for example, if the question comes for 5 marks, maximum you can score 3 or 3.5 marks. But if you write the resonance structures of the carbocation, then you will score full marks. Now let's jump into the topic. So aromatic electrophilic substitution reactions of benzene involves 3 steps. In the first step, the given electrophilic reagent undergo dissociation and thus it generates electrophile and base. So if you consider YZ as the electrophilic reagent, it dissociates to give Y plus and Z minus. So here Y plus is the electrophile. Now in the second step, the formed electrophile, it attacks benzene ring system. So here the molecular formula of benzene is written, that is C6H6. So what happens here? Y plus attacks the aromatic carbon. So here we have written C6H5 hydrogen. One of the hydrogen from benzene is written separately and Y will be attached here. That is the electrophile will be attached. So that is how we get the resulting carbocation. So this carbocation is also known as benzenonium ion or arenium ion. Now once this arenium ion forms, immediately it undergoes deprotonation by the action of base and that is how finally it gives corresponding substituted benzene. This mechanism was explained by taking nitration of benzene as an example in one of my previous video. The link for that video is provided in the description. So the rate determining step involved in this entire reaction is second step, that is formation of carbocation. Okay, now let's see how we can draw these resonance structures. So here I'll be explaining the resonance structures of the resulting carbocation by taking general reaction of benzene as an example. So this is the structure of benzene and Y plus is the electrophile which is generated in the first step. Now this Y plus can be nitronium ion, that is NO2 plus ion in case of nitration reaction, and it can be sulfur trioxide in case of sulfonation reaction. And while in case of halogenation, if you consider chlorination as a model example, then chloronium ion Cl plus positively charged chloronium ion will be acting as electrophile. Now coming to Friedel-Crafts alkylation, alkyl cations, that is R plus ions are considered to be electrophiles, and in case of Friedel-Crafts acylation, acylium ion, that is RCO plus ion will be acting as electrophile. These are the various electrophiles generated during specific aromatic electrophilic substitution reactions of benzene. Now let's see how we can draw the resonance structures for this carbocation. So first I have written the structure of benzene, okay, and then number the benzene carbon atoms so that you can easily understand the drawing of resonance structures. Then this is the structure of electrophile. Now what happens? While making a bond, this electrophile will be utilizing one of the doubly bonded electrons of benzene. Let us say the double bond which is present at first position is utilized to make a bond with the electrophile. That means we want to show the point of attack at first carbon atom. At each carbon atom, benzene will be having one hydrogen. Because now we are showing the electrophilic attack at first carbon atom, I have here separately shown the presence of hydrogen at first carbon atom. Because we know that there will be 3 resonance structures possible for the resulting carbocation. So I have just made a hexagon ring system here with hydrogens represented at the first position. So like that I have drawn 3 structures because we know that the resulting carbocation has 3 resonance structures. When electrophile attacks on first carbon, it utilizes doubly bonded electrons present at first position and thus the Y plus ion, okay, that is the electrophile, will make a bond at first carbon atom. So attach that Y group at first carbon of the benzene ring system. Okay. Now that we have attached, this group will be present on first carbon constantly in all the resonance structures. Okay. So attach this Y group at first position in all the resulting resonance structure. Okay. Electrophile is utilizing this doubly bonded electrons. Now the second carbon which is previously holding the doubly bonded electrons becomes electron deficient. So that is the reason second carbon atom here attains positive charge. So keep a positive charge at second carbon. Now coming to the other structural features, we are not disturbing the double bond present at third and fifth position. So keep these double bonds as it is as that of the benzene structure. Okay, while writing the first resonance structures, keep these two double bonds same as that of the benzene structure. So that is how we get resonance structure 1. So in this resonance structure, positive charge is present at second position. So to remove the positive charge present at second position, we can transfer the double bond which is present at third position to second position. Okay, so that is how the positive charge which is present at the second position can be removed. So when we transfer this double bond, now in the resulting resonance structure, there will be a new double bond between 2 and 3 positions. Okay. Because now fourth carbon, previous structure, it is having doubly bonded electrons, but in the resulting structure, the double bond has been transferred. So because of that reason, the fourth carbon becomes electron deficient and thus it attains positive charge. So keep plus symbol on the fourth carbon atom. Okay, now coming to the other double bond, that is double bond present at fifth position, is undisturbed. We are not disturbing that double bond. So keep that double bond as it is in the newly formed resonance structure. Okay, so this is the old double bond and the remaining structure we have written same as that of first structure. Only what is the difference that we made? The double bond which is present at third position, we have shifted to second position and positive charge on the fourth carbon atom. Okay, so this is how we get second resonance structure. Now, how we can draw the next resonance structure is, in this structure, positive charge is present at fourth position. So to remove the positive charge present at fourth position, now shift the double bond which is present at fifth position to the fourth position, so that the resulting carbocation will be now attaining a double bond at fourth position. Okay. Now when we shift that double bond, obviously the sixth carbon atom becomes electron deficient. Okay. And thus it attains positive charge at sixth carbon atom, while the other double bond which is present at second position is unchanged. So write the same double bond in the newly formed resonance structure. So this is how we get the third resonance structure. Okay. Now if you further to remove the positive charge from sixth position, if you shift this double bond to here, what happens? We get structure 2. Okay. Again back we get structure 1. That means for the resulting carbocation, only these 3 resonance structures are possible. Because all the resonance structures are chemically equivalent, we'll show them with double-sided arrow. Between the couple of resonance structures, we will keep double-sided arrow. And all these structures are shown within a square bracket. So this is how we will represent resonance structures. Now all these resonance structures can be represented with the help of resonance hybrid. Now let's see how we can draw resonance hybrid structure. So to write the resonance hybrid structure, we will keep this kind of symbol. Okay, either you can keep 3 bonds, okay, or you can keep a double bond with this type of sign. It means it is equivalent. That means all the 3 resonance structures are equivalent to the resonance hybrid structure, whatever we are going to draw. All these resonance structures are having a cyclohexane ring system, okay, with H and Y group at first carbon atom. Okay, so this is the common structure feature. So write that part first. Okay, on each of these resonance structures, if you see, they are having at least 2 double bonds. This resonance structure is having at third and fifth position, and this structure is having at second and fifth position, and this structure is having at second and fourth position. So if you combine all these structural features together, it is like the double bond is migrating between 2 to 6 carbon atoms. Okay, that means the relocalization of pi electrons is observed between 2 to 6 carbon atoms on this aromatic ring system. So to represent that, just give a dotted circle. Okay, so that can be represented with a dotted line or dotted circle. Okay, so which covers 2 to 6 carbon atoms. Okay, and another common structural feature in all these resonance structures is positive charge. In the first resonance structure, it is at second position. Second structure is at fourth position, and in the third structure, positive charge is at sixth carbon atom. That means the positive charge is migrated on alternative carbon atoms. Okay, so to represent that, we'll keep a positive charge in the center. So this is how the resulting carbocation resonance hybrid structure will be shown. This way of writing also, if you feel difficult, I'll give you another simple tip. Because you know cyclohexane ring system, first bake cyclohexane ring systems, 3 ring structures. Okay, and represent hydrogen at first position. Now you know that positive charge is present at second, fourth and sixth position. So keep the positive charge alternatively at fourth position on the second structure and at sixth position on the third structure. Just after completing that, try to accommodate the double bonds. Okay, so you cannot keep double bond at first position. Okay, because it is already tetravalent carbon. Okay, already 4 bonds are there for carbon. Okay, now second position is holding positive charge, so you cannot keep double bond there. So what are the rest all positions? You have to keep between 3 to 6 carbon atoms only in the first structure. And always will keep double bonds alternative positions. That means the leftover possibility is definitely you have to keep a double bond at third position and fifth position. There is no other alternative. Okay. Similarly, the second resonance structure also. We should not disturb first carbon and fourth carbon. These two carbons, we cannot show double bonds. So what are the leftover carbon atoms? It is 2, 3 and 5, 6. And hence, we will keep double bonds there only. Okay. Coming to the third resonance structure, it has already first carbon tetravalent. Okay. And sixth carbon is positive. So avoid 1, 6 positions. Okay. So between 2 and 5 carbon atoms, now you show double bonds at alternative positions. Okay. So if you cannot understand exactly that movement of double bonds and positive charge, logically also you can think, just remember, you have to write the cyclohexane ring system with a tetravalent carbon at first position. Now alternatively move the positive charge 2, 4 and 6 positions. So try to accommodate the double bonds in the remaining possibilities. Okay, in that way also you can easily draw these resonance structures. Polynuclear aromatic hydrocarbons such as naphthalene, anthracene, phenanthrene and heterocyclic compounds like furan, thiophene, pyrrole. These molecules also aromatic in nature. That is the reason they will also undergo aromatic electrophilic substitution reactions similar to benzene. So once you learn how to draw these resonance structures in case of benzene reactions, then you can easily learn the reactions of those polynuclear aromatic hydrocarbons and also heterocyclic compounds. So if this concept gone deep, then give it a like, subscribe my channel so that you will never miss my next coming chemistry concepts. So in the next coming video, I'll be explaining why toluene is more reactive than nitrobenzene. Thanks for watching and stay tuned to my next video.